My pleasure to introduce our next speaker, Frank Wood, who will be talking about very interesting work on how to use deep learning for inference.
Thanks, Vikash, and thanks for putting on this, all of you, the organizers, everybody, for putting on this, what is a spectacular community event. I think it's wonderful. Indeed, first of all, you may know me from Oxford. I'm not there anymore. I've moved to UBC, where the grass is greener and the hills are higher. So let's go into the Wayback Machine for a second and think about probabilistic programming, 2014, 2015, before the first international conference on probabilistic programming, something like that. And I would say that there were sort of some obvious or emerged trends, which is to say that there were a family of what I would call restricted in some way programming languages like Stan, Bugs, Infer.net, which basically are reposed on fixed computational graphs and mean that they allow for the denotation of an easier, in some sense, inference problems, leading to fast inference algorithms or faster inference algorithms, so on and so forth. But it makes it a little bit difficult for users to code some models or impossible for some other models. But it doesn't really matter. These languages are awesome. They're cool. And when I tell people what to use, I say Stan, Infer.net, something like that. If you're doing statistics, no question. At the time, there were also these crazy people who were working on these unrestricted languages, like Anglican Web People, Venture, so on and so forth, which made it possible for users to denote all kinds of models, led to really hard inference problems, meaning slow and impractical. And they correspond in the graphical model, in the neural net language, to things like dynamic computation graphs, so on and so forth. In general, all of these languages, and at that time, everybody was focused on fixed, trusted model, one-shot inference, okay? Really doing statistics rather than AI or something like that. Now there's some bleed through, so on and so forth. This is, since then there has been a really interesting trend in probabilistic programming, and I think Josh has perfectly said it better than I could possibly say it, that the stuff that's been going on since then and through that time, so on and so forth, has basically taken us from the upper left of this corner. By the way, is Zubin here? He's not here, he's taken off, okay, good, then I can really make fun of him because I propose to this community that we refer to diagrams like this as Zubin diagrams, because if you've read any of his papers, you know that every gosh darn one of his papers has one of these diagrams in it, which is always, here are all the possible quadrants and things in those quadrants. So. And Garamani is too hard to remember how to spell, so let's just call them Zubin diagrams, okay? In the upper left-hand corner here, we have one-shot inference and a fully specified model. This is where probabilistic programming was for a long time. And then probabilistic programming has been taking this tour where we say, okay, well, maybe we know the model, we believe in the model still, but actually we want to do something AI-like. This is sort of the inference in a simulator kind of game that we all like to play, but we'd like it to be fast. We want to do AI-type things, and we want repeated inference to be fast. And of course, if we don't know the model and we actually want to simultaneously learn the model, this is where I think probabilistic programming and deep learning are running into each other in the guise of or semi-supervised deep learning or structured variational autoencoders plus probabilistic programming or whatever. So we're on this grand tour together, and where you stick doesn't really matter, it's all cool, but I'm going to sort of talk about some of our work on this path and maybe point out some key things that some of the students that I've worked with and postdocs that I've worked with have pointed out to me that we should pay attention to while we're on this path. Okay, so we've already mentioned one of the big problems, that's sort of hidden in this room. We don't like to talk about it. We all know it's there, but we don't want to admit it really. Bayesian inference sucks. I mean, it's a great way to frame problems. We like to think this way. It's super clarifying. I would call myself a Bayesian, but it's slow, right? And this has led to a lot of work in various fields on amortized inference or compiled inference or so on and so forth. And I'll talk a little bit about the background there and give some types of approaches in probabilistic programming and some examples in first and higher order languages. We'll also say there's another problem we should think about, which is that when we're doing any of this amortized inference stuff, or even just any kind of neural network work at all, we know that we basically have no idea where the structures of these neural networks come from, right? So there's an opportunity to use some of the probabilistic reasoning or reasoning about the structure of probabilistic graphical models, denoted as programs, to guide our choice about neural network architecture. And of course, we also know the last thing that's kind of unpleasant about this entire thing is that we're the only people in the world also that can write models in the languages that we make, really, right? And most people just want to start with a big tabular data set and say, give me some insight or make some predictions or something like that. So writing models is really, really hard, and I think it's really exciting to think about and maybe most appropriate if we really want to have the kind of widespread appeal that, that many of the other communities in machine learning benefit from, to think it really hard about simultaneous model learning. And here I'll go through a couple of lessons that we learned trying to get into this game that basically suggest that some of the old ideas from way back are really, really good ideas. So I don't know who wrote this, whether it was Andreas or Noah. Noah, did you write this? Or you wrote that? I figured you probably wrote the abstract. I keep using it. It's the worst design slide that I use, but I use it over and over and over again because I think it's really elegantly written. And I think it gets right to the point of if we don't want to do statistics and we want to do repeated fast inference and we want to still be Bayesian, so on and so forth, here's the idea. Bayesian inference is computationally expensive. Even, sampling algorithms, the ones that we, write, so on and so forth, take forever to produce reasonable answers. In contrast, we as humans do scene recognition and so on and so forth very, very quickly, basically in a single pass from perceptual evidence to deeper interpretation. Can we build systems that exhibit similarly rapid performance? So that's really what this talk is about and some of the lessons that we've learned. Mathematically, it's like this. Over here, we have a probabilistic program on the left-hand side, sorry. So we've got some latents x, these are the random variables in the program, we've got some observed quantities y, and the probabilistic program denotes both the joint distribution and the conditioning opportunities. But what we would like is this thing over here, which is some sort of machine, some thing that takes our observation and directly maps to our posterior distribution over on our latent quantities, okay? So this thing, we're gonna parameterize by phi. For most of the time here, it's going to be a neural network. The structure of that neural network could be whatever. It could be a program. It could be, who knows? There's all sorts of interesting ideas. But in this is mostly going to be deep neural networks. Okay. There are lots of related ideas about trying to do inference fast, in particular repeated inference fast. Of course, we should keep in mind that when we're trying to do repeated inference fast, particularly for statisticians, there's a little bit of a chicken and egg problem because you want to be able to do inference fast, but in order to solve the inference fast problem, you have to learn something to do inference fast, and then you waste all the time learning that thing. So really, we're in this repeated inference setting, right? That's where it is. But there are a bunch of people in statistics who have been working on this, in particular, thinking about deriving optimal proposals for importance sampling. There's, of course, all of this stuff in modern variational inference. And I could write 20 slides of references here, so I apologize if I've left anything off. But of course, in this community and others, there have been some really, really nice work, particularly in computer vision. Obviously, Vikash and Tejas and Josh have been thinking about this for a long time as well. But really, I mean, people have been thinking about this in the AI context for a really, really long time. The idea that there's a model and also a very fast inference architecture to go along with it, the wake-sleep algorithm, the Helmholtz machine, so on and so forth, is really, it's part and parcel with the ideas that I'm talking about today. In our community, we have a little bit of a confusing set of names that I'll try to clarify. I think these names are all horrible and probably confusing for a number of you. But let me say what's been, from my perspective, which could be wrong. I look forward to interactions to clarify further. But in our community, I think that there's been kind of two independent but complementary efforts to do this amortized inference thingy, one of which is, goes under the name of guide programs. And I'm going to use this as my name for approaches which attempt to learn an inference artifact by minimizing this KL divergence, the VB variational-based KL divergence, which looks like this. In other words, basically, we're going to try to make Q phi really close to P of theta of x given y, or inference networks, which has a different objective over here, the opposite KL, but has the same, tries to do the same thing, tries to make Q phi as close to the posterior as possible, okay? And this, of course, relates to all of the stuff that we know about mode seeking versus mode covering kinds of stuff, so on and so forth. I'd like to call out my graduating student Tuanan's notes. He has lovely, lovely notes on this. Anyway, so this is not the only distinction between guide programs and inference networks, but the point is that there are a couple of different objectives that you could use to try to produce such an artifact. And there are kind of two separate trains of papers. And I'm going to start talking about this, and then we'll talk a little bit more about this later. So to train an inference network is actually pretty straightforward. When you write this thing down and you do a teeny bit of algebra, you basically get that there's an expectation over the joint distribution under the model of this thing. Of course, this is a regression or classification loss. Basically, it's how you train neural networks. I'll point this out later. This thing doesn't require any sort of reparameterization. You can train on samples from the model. But critically, and this is a major problem, it learns to invert the model, right? Okay? But that's okay because when we're probabilistic programming people, we write down the model, and sometimes we actually believe the model, right? Okay? Sometimes. Okay, so let's look at how this looks. What's the recipe for doing this kind of inference compilation thing? And this is work by Brooks, who gave a talk, an awesome talk yesterday and could have talked about this, where we basically did this for first-order probabilistic programs. So again, there's a correspondence between first-order probabilistic programs and graphical models. You can compile them one to the other. So let's say we have the compiled artifact, and this happens to correspond to a heavy-tailed polynomial regression model that doesn't have a closed-form posterior. Okay? Fine. So Laplace priors on the weights and a student t distribution on the likelihoods. And what we'd like to do is we'd like to learn the posterior distribution of the weights of this polynomial function. Okay? We'd like to somehow do something with this graphical model that turns it around such that we get a computational artifact that goes from what we see to what we don't see. Arrows in the other direction, right? And then we'd like to somehow go from that to some sort of actual neural net instantiation which has some architectural choices that so on and so forth. And then we need to train this thing using this objective. So basically we sample from the joint distribution, compute this guy, and then magically at the very end of the day we have this Q phi which it does this. Okay? So each row of this is a new data set. Here's a ground truth posterior from Metropolis, computed via a standard Metropolis Hastings long run chain. Here's the prior. Again, this is a polynomial regression model with heavy-tailed distribution on the weight, so the prior is quite diffuse. Basically what you get is you shove in these black data points, and bingo, bango, what you get out is a neural net that is some weird approximation to the posterior. Okay? Now the inference compilation approach also happens to be compatible with asymptotically exact inference, which is to say that you can clean up all of these samples using important sampling. So basically you can reweight them by computing the probability under the joint distribution denoted by the original program and get an asymptotically exact answer as you generate more and more samples from this network. Okay. So that's, yep, 5 minutes. That's funny. Okay, cool. All right, okay. So what do we do when there's no probabilistic program or graphical model correspondence? You can't invert the graphical model. The structure of the inference network must match any generative model. It must produce answers for the addresses at runtime. So what are the options when you do this? Basically, there are a couple of options, and they're different between the inference comp and the guide program community so far. One is, this is another axis of variation, one is that you can manually program the guide program in some kind of a way, custom bespoke or something like that, or you can, for instance, commingle source code with the generative model source code so that you get alignment at addresses. Or you can sort of have two separate code bases where you have to match the addresses somehow magically or require the user to do that. Or you can be super automatic and use a very, very generic but powerful regressor that dynamically generates required addresses at runtime. And given that I only have 5 minutes, it means I'm only going to get through the first third of my talk, which is unfortunate, but at least I can get through this part, which is to say, here's what a guide program looks like, and this is what Daniel Ritchie, who also gave an awesome talk yesterday, and Noah did as a precursor, I think, to the thinking that went into Pyro, I think that's fair to say, where here we have a generative model, and at the same time you actually write a guide program outlined here in blue. This is taken directly from their paper, which has the same control as the original program, but different data flow. It samples the same random choices as the simulator in the same order, but the data flowing into those is different than the choices than the data flow before. Okay, so here we have a guide program and a regular program programmed together. That's a little bit confusing. That's cool. And you can train it with either objective, and that's neat. And the alternative approach which we've taken is to basically use ridiculous deep learning networks, basically, in really generic polymorphic inference networks. So to give you an example of what's going on in our networks, we say our network is going to be required to give us a proposal value at whatever address the generative model program produces at whatever given time. Okay, so the classic CAPTCHA example, which we all owe Vikash and crew a huge thanks for, because God knows no prob talk is complete without a CAPTCHA example. Basically what's going on here is we want to do inference in this model where we care about the length of the CAPTCHA and in particular like what characters are in the CAPTCHA. There's some observed CAPTCHA, there's an embedder, and then basically what we have is an LSTM that takes a couple of things, like for instance the address of the sample, the instance, and the type, so on and so forth, pushes it through some very complicated stacked LSTM, and then pushes it out a polymorphic proposal layer that has something to do with the type and the address to produce a proposed value. Okay? Then this gets chucked back in an RNN style way with new address information arising from running this generative model. And gets chucked out, and we make another proposal here. Okay, so this is trained in exactly the same way, and what this really kind of looks like at the end of the day is a neural programmer or something like that, where you know the entire execution trace of the program, and you get to condition on both this, and all you care about are learning all the weights of this crazy LSTM thing. But at the end of the day, when you couple this to the original probabilistic program, you can do amortized inference in a higher order probabilistic programming way, in a way that enables asymptotically exact inference. Okay, and it works, and there's kind of an interesting thing that suggests something about the regression nature of this. And there's an interesting rule of thumb. So here, basically, we say, okay, look, you write a probabilistic program that generates something, a CAPTCHA of these various styles. It's like a 3-line change from one to the other. You sit and you press compile, and then basically you get, human perception, speed, inference, with very high recognition rates. But the kind of fun thing that it's a, this is the kind of thing that you sort of take home and think about just a little bit. These inference networks begin to saturate when you have enough training data, when the amount of training data is approximately equal to the number of parameters in the inference network. Okay? So if you think about this as just a straight up regression, right? How many data points do you need in order to not overfit? Same, duh, okay? So really what's going on is, what's kind of cool about this sleep part of the wake-sleep algorithm is that we generate data from our model. But that means we have an infinite source of data, which means our inference network can basically be as complex as we want, provided that we're willing to wait long enough to train it. Okay? So that's basically what's going on here. This is the number of training traces, and this is how good it does. And this is about the number of parameters in the neural network. It's an interesting rule of thumb. I'm running out of time, so again, I'll stop with the first third of the talk. But I'll point out that you can take this a long ways. Okay, and I think if you've read any of the stuff that I do, I tend to take kind of a gross view of things, like do a lot of operating system stuff and crazy stuff like that. I would like to point out that one of the things that I think we're doing a little bit wrong, particularly in the AI side of things, if we want to, let's step back from the AI side of things and say we want to do statistics using simulators. Okay. There are a huge number of existing simulator code bases that are not written in Hack or Pyro or whatever. They're written in an existing programming language, and we'd like to be able to do inference using those. So I'm really excited about this. It's going to get rejected like everything in machine learning does. But basically, we have a big collaboration going on where we're trying to push this basically as far as you can possibly go, where you can think about the inference network as being this puppet that's controlling a generative model simulator program that's been very, very, very lightly instrumented. In particular, what we're going to do is what we have done is instrument SHERPA and a subset of GÉANT. SHERPA is the C++ source code that represents the standard model and all the particle interactions that can take place in that. And GÉANT is the engineering simulator for the Large Hadron Collider Atlas detector. Okay? So In doing this, we have done my postdoc, Gunnar Biden, has done a huge amount of engineering, which is distinct from the Pyro family of things or the Edward set of things, where basically there is a language for doing inference compilation control called PyProb that interfaces to any code and any simulator in any other language actually over a network, so on and so forth, and treats that controlled program as basically a black box with a very, very small amount of instrumentation. And I guess before I go to my conclusion slide, I will say that we've had some pretty serious success with this, and I think we can demonstrate or generate a nice demonstration application for the community where basically, oh, by the way, this is what I wanted to name the paper, but SHERPA, SHERPA is this million-plus line piece of code that is the standard model. It's crazy. Physicists, this is great. You'll love this. This is the operating system thing. Physicists wrote this entire thing with only uniform 0-1 random variables. There's no notion of a standard normal. There's no notion of a Poisson draw. There's none of the stuff that we want. Physicists are like, screw it. I've got uniform 0-1. Anytime I need a normal variable, I'm just going to write the transformation code myself in place. Seriously, it's crazy. Okay, all right. But this actually says, wait a second, maybe we need to think about this and actually think, this goes right back to the statistics interface to stuff. What do you really need? You need access to a random number generator, you need to draw some random numbers, and then you generate some stuff at the end, okay? So what we have been able to do, though, is basically, it's the first ever inference using the LHC generative model software stack, and it's thousands and thousands and thousands, doing the inference compilation thing is thousands and thousands of times more efficient than doing some sort of Metropolis Hastings or whatever kind of inference in this stack. So basically you start with a detector output and you go back to which particles, when, where, what particle decomposition pathways through this crazy Feynman diagram universe gave rise to this observed signal. Okay? So this is the kind of thing that we can do. This is not an AI application. I care about AI applications, but we can do this using the tools of amortized inference. I'm out of time. All right, really. So I'll leave it actually here. I won't even go to my conclusion slide, but I will point out, this is very important, that this amortized inference thing, so like Jan LeCun is actually right? Joshua Bengio is right. Deep neural networks are doing inference, okay? And if you look at all of these results, which you probably know from the popular press and so on and so forth, what's common to them all is that they're actually trained using synthetic data, okay? So you have a synthetic data generating program used to train a regressor to predict values in that program, okay? That is important sampling style inference compilation for a probabilistic program, okay? So there is this other community that's doing exactly this thing. This is, we should pay attention to it, and I think it's really, really interesting. Like a super interesting question is, why do these constant time algorithms actually work, right? That's a super interesting question. All right, thank you very much for your time. Apparently I had time for one question. I have a whole list of questions. I can put them up for you. You can choose from it if you want to. Ken, I can't see you. Oh, there you go. Hi.
Anyway, are your neural nets or compilation neural nets as hard to train as deep learning neural nets, or are they same? Are they just difficult to train?
This is an interesting question. They're marginally. They're no more difficult to train. Stochastic gradient descent works just fine. They're marginally more difficult to wire into the existing software tool chains, because the existing software tool chains don't do well with neural nets that are polymorphic. Basically, they expect a constant size vector or constant size structural representation of the parameters in the neural network, and this doesn't have that on a per trace basis, so it's very difficult to batch and these kinds of things. So engineering-wise, much harder to train. Science-wise, totally equivalent, basically. Thank you very much.